Hello again. This is Math 2233 coming to you from the College of DuPage, and the title of this lecture is Projectile Motion. And be an active learner as you watch this video. By way of introduction, you probably encountered projectile motion before. And an example of projectile motion, and this is supposed to be a piano. And so we shot a piano out of a cannon and it went up, but then it went down and it crashed in some pieces. And here's a guy who just has his boxer briefs, I guess on. But anyway, you see that this did go up and come down, and it is more or less a parabola. In fact, we will see in our lecture that this is a parabola. So this does, the trajectory of the piano is in a plane, and it goes up and it goes down, and it goes up and goes down, but it also has a component, which is a vector that's a horizontal component. So that's a little bit of an introduction, but then there's a fact from physics that you need to understand. And the fact from physics is shown in this other thing where we have a strobe light that's flashing on and off with a timer. And so each one of these flashes is the same instant in time. And what this shows is just this little apparatus dropping the red ball, but it kicks the yellow ball out with a little bit of a horizontal thing. So it kicks it out, but what you should notice is that the falling is exactly the same. So the takeaway from this drawing, from the strobe photograph, you probably did this experiment in your physics class, but the takeaway of this is that the horizontal and vertical components, if you're ignoring air resistance, is the same. And we're just going to, for now anyway, ignore air resistance. In my differential equations class, we do problems where we incorporate air resistance. It's a harder problem that way, but you know, that's what we do in that class. But here we're talking about ignoring air resistance, and so the horizontal and vertical components are independent one with another. That will be important as we go through. Okay, so that is enough of introduction. So we'll talk about projectile motion, and we'll talk about this. A projectile is fired with an angle of elevation alpha. So you see that's the picture that we get here. And so we have the angle of elevation is alpha from the horizontal, and initial velocity v0. Now note that v0 is bold-faced, so that is a vector. So this is a vector. It has horizontal and vertical components. And you're assuming that the air resistance is negligible. That's important. And that the only external force is due to gravity. You see, air resistance isn't affecting the horizontal motion, but you're going up, but then you're coming down. Gravity is affecting you actually when you're going up and when you're going down. So the only external force is due to gravity, and you want to find the position vector r of t, position function r of t, of the projectile. What is the value that of alpha that maximizes the range, the horizontal distance traveled? And if we were doing this in class, we might do some experiments and stuff like that, and you probably have already guessed the answer, but that's the problem that we're going to address. But in the course of that, what we're going to do is we're going to derive equations for this motion. So that's what is at hand. So here we go. Please follow along and make sure you verify the calculations, that you understand what's happening. Okay, we set up the axes so that the projectile is starting at 0, 0. We have that freedom, and that simplifies calculations. And since the force due to gravity is downward, we have capital F, this is a vector, is m, the mass times a. This is known as Newton's second law. So the net force is equal to m times a. And the acceleration is the acceleration due to gravity. It's in the y direction because of the way we set up our coordinates. And so F is equal to minus mgj. And we're taking down to be a negative number here. That was arbitrary, but that's the way we're choosing it to be. And the magnitude of g here, which is the acceleration due to gravity, is the magnitude of a. and that is approximately, and actually you see we factor the g out as a scalar, so g is the magnitude of the acceleration, and that is approximately 9.8. In your physics class at the College of DuPage, you call it 9.81, and that is meters per second squared. So the acceleration is, and the way we get that is we set these two things equal and we cancel out the masses on both sides of the equation because it's not zero. And we get that acceleration is minus g in the j direction. But also, v prime is a, so we could just put v prime is a, and so what we do is, but if we integrate a, we get the velocity. So we integrate both sides of this with respect to t, and we get this. So v of t is equal to minus g. The t comes from the integration plus c. Now that c is a constant of integration, but it's an integration vector, and that c is what we get when t is equal to 0. And so that's really my initial vector. V sub 0 is what c is. Therefore, r prime of t, which is another way to call v of t, is equal to that, and now we've identified our constant as being v0. Now we're going to integrate this again. Well, if you integrate this derivative, you get r of t. When you integrate this, t is the variable of integration, and so you add 1 to the exponent, divide by the new exponent, so it is minus 1/2 gt squared in the j direction. Plus this v0 is a constant vector, so we integrate that. That's integrating 1 as the scalar multiple there, so you just get t. And now you get another vector, which is d, which is the vector of the constant of integration. But in our problem, the way we set up the coordinate system, we started at 0, 0. So d is equal to r at 0, and that is the 0 vector. So the position vector of the projectile is given by r of t is equal to minus 1/2 gt squared in the j direction plus t times the vector v0. And if we recognize that the vector v0 has a magnitude of v0, then, and that's the initial speed of the projectile, then we can rewrite this way. And you see what we're really doing here, we're resolving the vector v0 into its horizontal and vertical components, and that means we're using cosine alpha and sine alpha. And so our earlier equation then becomes r of t then is equal to v0 cosine alpha t in the I direction plus this expression in the j direction. You see, this is what I'm using for v0, and if you do the algebra, you will get this. Now that means if I'm talking about the parametric equations, then x is equal to v0 cosine alpha t, and y in the j direction is v0 sine alpha t minus 1/2 gt squared. Now, the horizontal distance, and distance is equal to rate times time, of x when y is equal to 0. Setting y equals 0, we obtain t equals 0, or, and so you see what we're doing here is we're just plugging into this. Okay, so alpha, and I guess we're just having cosine alpha, but we're saying that we're letting y to be 0, and if y to be 0, that tells us that t is equal to 0 or t is equal to this number. So either at the start or the finish, you're going to be there with y being 0. So we can solve that. This is what we get when we substitute those values in. And then I can simplify this. You see I got v0 times v0, that's v0 squared. I have all of these things in here. I'm using a trig identity. This is 2 sine alpha cosine alpha is sine of 2 alpha. And so this is what the distance is. So the distance, the horizontal distance, which we were trying to find, has its maximum when? You see, this is usually, or in fact, this is usually less than 1. And when is it equal to 1? Sine of 2 alpha. That happens when alpha is 45 degrees. And that probably satisfies your intuition very well. And you say, oh, okay, that's what's happening. And having something at 45 degrees will maximize the distance that it will that it will go. Okay, now what we can do is then we can go back to what is equation 4. And by the way, this is equation 4. Down here, I rewrote it for you. So this is the parametric representation. What we have is that y, and we're going to eliminate t. So what you do is you say t is equal to x over v0 cosine alpha. So you solve this for t, and then you substitute that value of t in here. But you see that means it's going to be a quadratic equation. In fact, you can see that this is a quadratic equation already in t, but it becomes a quadratic equation. It's a quadratic equation in t this way, but when you substitute there, what you're going to have is a quadratic equation in x. Okay, so with all that, here's a problem for you to do. A projectile is fired with a muzzle velocity of 150 meters per second and an angle of elevation of 45 degrees from a position 10 meters above ground level. Now we've changed things a little bit. This is a position of 10 meters above ground level. Where does the projectile hit the ground and with what speed? There's two questions. Where does it hit the ground and with what speed? I really like these problems, so make sure that you can do this. You know what to do. Let's see how you did. Okay, we placed the origin at ground level, so the initial position is 0, 10. So we need to adjust the equation by adding 10 to the expression for y. And we're taking these values. This is V0 is 150 meters per second, alpha is 45, g is 9.8 meters per second squared, and we get that x is equal to, we plug in the values into that thing that was called equation 4, and we get 75 times the square root of 2t. That's the exact answer. And y is, after you simplify, it is this. And notice that at first you're going up, there is an upward component, but then eventually you're going down because of the gravity. That's the sign convention that we used, and that's the SIGN convention that we use, and this is what we get for our y equation. Now impact happens when y is equal to 0. So we set y equal to 0, and that means we're setting this equal to 0, and you have to use the quadratic formula, and I would expect you to be able to do that and solve the equation. And you're only taking the positive value of t because time in our world can't be negative, and so we get this. So it's approximately almost 22 seconds. This is what it is rounded to the nearest hundredth. But there was another question. The other question we wanted to know was, how fast is it going? Well, this is where it lands. So it lands a little bit over 2,300 feet from where we started. So it hits the ground that distance away, but the velocity is given by, I take the derivative of the equation that I had before. For r of t, I get this equation, and so I know what t is. T was the number that we had before. We substitute it in, and it said with what speed does it hit the ground. So this is the magnitude of that, and we get this as approximately 151 meters per second. An excellent application. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.